So electron flow in a capacitive circuit, we started out with the circuit just as it's been connected to some form of energy, a battery in this case. Initially we don't have any charge on the capacitor at all. When it's connected to a battery, we start to get electrons flowing from this negative terminal round to one plate of the capacitor. Remember that in the middle here there's an insulator, so we don't have any flow of electricity there at all. So we get a build-up of negative charge on here. It starts to build up there. Any negative charges that are on this side, on this plate, begin to be pushed away because like charges repel and unlike charges attract. So those negative charges get pushed back round to the battery here. So what we see in purple there is really the flow of electrons, the movement of negative charges, which we know as electric current. So we've still got a flow of electric current there. Charge is beginning to build up on both of the plates there. A little while later, we've still got electrons moving round and building up here. They can't again flow across this gap because that's an insulator. So we get more and more negative charges building up here, which means we've got more and more of a repulsive force pushing negative charges that are on this side back round to the battery. But more and more of those charges are building up here on this one plate, so there's less negative charges to move around, and therefore there's less electric current flowing. So that's what we indicate by the dotted line, is the fact that the current is reduced. But because we've got more charge here, we've got more negative charges here, more positive charges here, we've got more charge across the capacitor, which means that we've got more voltage across the capacitor, because one of the first things we looked at was the relationship between charge and voltage in a capacitor, and we realised that they were directly proportional. So if you've got more charge here, then you've got more voltage across there, so we've got a greater potential difference as the charge increases. Eventually we've got all of our negative charges that are available to carry the electricity being built up on this one plate, and so therefore all the positive charge is on this plate, and we've got no electric current flowing. So we've got no electricity flowing around here because we've got no negative charges to carry that electricity, but we do have lots and lots of charge here, and because we've got the more charge, the more voltage we have, it means we've got the maximum potential difference across here. So say for example, we've got 5 volts here as our voltage supply, then it means that once this capacitor is fully charged, we'll have the full 5 volts across here. We've got a charge difference here, which means we've got a potential difference. We went from there to start talking about energy stored in a capacitor. We came back to this idea of charge being directly proportional to voltage. As I said, it can be shown by calculus that the area underneath this graph is equivalent to energy, but you don't need to know that, you just need to know this equation, that the area under the graph is a half QV and that energy is equal to a half QV. We can combine that with the previous equation that we've looked at, which is Q equals CV, to give us two other expressions. So I got you to do that. You substitute in for Q first of all, gives you a half CV squared. Substitute in for V the second time, and you get Q squared over C. So we end up with 3 different equations for energy in a capacitor. They can only be used for a capacitive circuit. They cannot be used in any other context. You need to be able to give derivations for these two here. So take that as your starting point, use Q equals CV with that, and you'll be able to derive these other 2 equations. So we know how electrons move in a capacitive circuit. That will help as we go further on in the topic. We've also now got 3 separate equations for energy.